So today I'm going to give you guys a brief overview of the dark matter problem in physics. So first we'll just answer the question of what is dark matter in the most basic of terms. We'll then look at some of the pieces of evidence in favor of dark matter. Why do we think it exists? Not just because it sounds cool, right? We'll discuss what might it be that makes up this dark matter, potential candidates. And then we'll wrap up, we'll see how can we identify the dark matter. Dark matter is something you can't see, so how do you detect what you can't see? And then we'll wrap up with our conclusions of where I see the field headed in the next 10 years or so. And so if you go to any talk by a cosmologist, pretty much guaranteed that the very first slide you're going to see is going to be some version of this one. The standard cosmology today, the best model we've been able to come up with for the universe, says that only a mere 4% of the matter and energy budget of the universe is made up by ordinary matter. So protons, neutrons, electrons, all the molecules that make up our bodies, all the stars and all the galaxies of the universe, add all that stuff up and it only accounts for about 4% of the matter and energy of the universe. About 73% is in the form of some mysterious dark energy. That'll have to be a talk for another time. And the remaining 23% is in this cold dark matter, which is what we're going to focus on today. And so, as I said, ordinary matter is a mere 4%. Apparently 96% of the universe is quite mysterious to us. And so, what is dark matter? In the simplest terms, we can say that it's dark. So it's non-luminous. It's not giving off light. It's not radiating electromagnetic radiation. It's dark. And we can say that it's matter. So it has mass. It interacts via gravity. That's really all we're saying. It has mass, so it interacts via gravity, and it's dark. It's not giving off light as far as we can see. That's all we need for dark matter. Now, why would we think that there is such dark matter out there? Well, we have to go all the way back to 1933. There was a great astronomer by the name of Fritz Zwicky, and he was looking at this cluster of galaxies. This is the Coma cluster. It's one of the largest clusters of galaxies on the sky. And he was looking at the speeds of these galaxies. These galaxies are in a gravitational system, and so they're all whizzing around one another. And so sometimes they're moving towards you and sometimes away. So if you've heard of the Doppler effect, we can use that shift to try and figure out how fast these galaxies are rotating. And so that's what Zwicky did. But he found out that as these galaxies are all whizzing around one another, well, gravity is only so strong. So if you go too fast, you'll escape. If you think about it here on Earth, we're bound by gravity. So if I threw a baseball, it would go across the room. If I threw the baseball harder, it would go further. And if I kept throwing the baseball harder and harder and harder, well, I throw it weak, it doesn't go too far. I throw it harder, it goes further. If I throw it really hard, I'll start to notice that the Earth is actually not flat, and that the Earth is round, and that it's landing further than I would expect it to land if the Earth were flat. And now if I throw it really, really, really hard at about 7 kilometers per second, I can throw it so fast that as it falls towards the Earth, it doesn't strike the Earth, and it goes into orbit. It starts to orbit around. And now if I throw it even faster than that, on Earth it would be about 11 kilometers per second that I would have to throw a baseball. But if I throw it really, really hard, it'll take off and it'll never come back. The gravity is just not strong enough to hold on to it. And so Fritz Zwicky found that that was the case with these galaxies. They're whizzing around so fast that their combined gravity shouldn't be able to hold on to them, and they should go flying apart. And so Zwicky comes up with really sort of a naive, simple solution. He just says, well, maybe there's more mass there, and we just don't see it. And this extra mass is providing more gravity, which is holding on to these galaxies and keeping the system bound together. And so he says, okay, so maybe there's just non-luminous mass there. And he's German, so he calls it Dunkelmaterie, or as we call it nowadays, dark matter. He says, apparently there's some missing mass. There's more gravity than what I expect. And so maybe it's coming from some matter that I didn't see. Now, Zwicky was a bit of a curmudgeon. He wasn't super popular with his colleagues. And so he had a string of brilliant insights that all went ignored for decades. So he predicted neutron stars, for instance. It was widely ignored. And he predicted dark matter here. And he was widely ignored. People paid very little attention to what he came out with here. And so he's basically ignored. For about 40 years, no one pays too much attention to what Zwicky had to say. This would change in the 1970s. And so fast forward about 40 years, and Vera Rubin and Ford and her other collaborators were studying spiral galaxies. And they were looking at how fast stars are moving around in these spiral galaxies. So again, we can think about the Doppler effect. We have a spiral galaxy, so all the stars are moving around like this. And so these stars would be headed towards me, and these stars would be headed away from me. So by the amount of blue shift versus red shift, I can figure out, well, how fast are things moving around in this galaxy? And so they do this, they're looking at a galaxy, and they're publishing what we would expect based off Newton's laws and Newtonian mechanics is that we would expect that as you get further and further away from the galaxy, that these rotation speeds should slow down. If you get further and further away from the galaxy, the force of gravity is getting weaker. And so the faster you go, the harder it is for it to hold on to you. And so if gravity is getting weaker, your rotation speed should be getting smaller too, or else you would just take off outside of the galaxy. And so this is what we expect just based off simple Newton's mechanics. But what they observed was very, very different. What they observed was not only do we not decrease as we expect, but the speed actually basically stays constant. The speed basically just doesn't drop off at all for this galaxy they were looking at. And so they said, well, that's awfully interesting, so let's go look at some more spiral galaxies and let's look at the rotation curves of these other spiral galaxies and see if we see the same thing. And lo and behold, they did. They saw the exact same thing in other spiral galaxies. And so here we have a nice big sample. Again, if we would expect from Newton's laws that all of these should be falling off to very low speeds as we get outside the galaxy. But instead they stay basically constant, or in some cases they're even increasing, which is very, very puzzling. And so for the context here, we need to know something about the size of the galaxy. And so the size of the galaxy here is only about 5 kiloparsecs. This would be all of the visible stars. And so the really, really interesting thing is not necessarily the stars themselves. Here in the first 5 kiloparsecs or so is where all the stars are. The really interesting stuff Vera and Ford and Rubin found was for clouds of gas that exist far beyond the galaxy. Out here, we would expect the speeds to be very, very low because we're about 5 times this distance away. And so we expect the speed to basically be approaching 0. And yet, even far, far outside the visible extent of these galaxies, the rotation curves are still staying constant. So how can we solve this problem? How can we solve this discrepancy? Well, maybe Newton's just wrong. Maybe our understanding of gravity, we just don't know enough about it yet. And so our expectations for these rotation curves, perhaps they're just wrong. That's option one, but it's not very compelling because Newton's laws have, of course, been tested extensively for several hundred years. Einstein came out with general relativity. We feel like we know pretty well what's going on with gravity. And so if Newton's right, and if we understand gravity, well, what's the implication? Well, perhaps there's some non-luminous matter that is providing the additional gravity that can explain why my rotation rate stays where it is. And so this then is the idea behind dark matter in our galaxy and in spiral galaxies, is that we would have the luminous galaxy that we see. In galaxies, there's also what are called globular clusters. Those are being represented here. But this would be all the ordinary matter, all the stars, all the gas, all the ordinary matter we can see would only make up about 5% of the mass of this galaxy. And then the rest would be a much, much, much larger dark matter halo that surrounds this entire galaxy. And so how does this solve things? Well, for those of us that have had introductory physics, which I think is hopefully everybody, when I'm looking around, you've seen that the orbital speed for an object goes like the square root of Newton's law constant times the mass divided by the radius at which you orbit. I think someone is in my Phys 221 class, so this should look very familiar to them. If I'm way, way outside the galaxy, here's my spiral galaxy, I'm a cloud of gas that's way out here, very far away from the galaxy. And so for me, this mass here should just be the mass of the galaxy. And as I get further away, my speed should decrease like 1 over r. But what we've seen is that this is not decreasing like 1 over the square root of r, instead it's staying constant. So how could I make this constant? One easy way would just be to say the mass is proportional to the radius. Maybe it's m naught times r. If my mass is proportional to my radius, well now I go and I calculate my orbital velocity, and what do you know? I'm going to get something that's constant. Alright, now my radius cancels out and I get something that's constant. So this is the idea. This is basically just the simplest way that I can solve this problem, is to assume that there's just more and more mass that I'm collecting that I just don't see. It's dark. And so this really launched the modern interest in dark matter in the 1970s. People had ignored Fritz Zwicky for years, but these were very firm observations that people found compelling, and so people became very interested in dark matter then in the 1970s. And so those are the two historically most important pieces of evidence. But today, if you're making the case for dark matter, they're far from the only pieces of evidence. We have several additional lines of evidence. They come from gravitational lensing. If you've ever heard anything about general relativity, you might know that light is bent when it encounters a massive object. And the more massive it is, the more it is bent. And so we can go out and we can look at the amount of gravitational lensing. And again, we see more lensing than we would expect if the only matter was the luminous matter. The cosmic microwave background is actually the best piece of evidence. This is the relic radiation left over from the Big Bang. Again, that's probably a topic for another day. But this is actually the best piece of evidence. We can look at cluster X-ray temperatures, the rate at which galaxies grow in the universe. We look at all these different pieces of evidence, and they're all pointing towards dark matter. And so right now, I just want to outline one piece of evidence that people have often referred to as a smoking gun for dark matter. And that's the bullet cluster, which is this picture I'm showing here. And so this is actually not one cluster, but two clusters of galaxies that have recently passed through one another. They've recently had an encounter. And now this galaxy is on its way off to the right, and this one is on its way off to the left after this encounter. And so we see the stars here, just in the normal picture, and now I've put over this pink region and this blue region. And so the pink region is very hot gas that's associated with this cluster, and it's glowing bright in the X-rays because it's so hot. And so it turns out that in a cluster of galaxies, most of the ordinary matter is not in stars, but it's actually in gas. There's about 15 times as much just gas as there is stars. And so what happens when these collisions happen is the stars are very unlikely to ever actually run into one another. The distance between stars is huge, it's several light years. So when these galaxies interact, they just pass right through one another. The odds of the galaxies colliding is very small. The gas, on the other hand, is in these huge clouds of gas that are very likely to smash into one another. So what has happened here is that the gas associated with this cluster has hit, you see a shock wave here, whereas from passing through the other cluster, this gas has been shocked. And then we see that on the other side, the gas associated with this cluster has moved on. And so most of the ordinary matter is here in the pink region. This is where 95% of the ordinary matter is. The blue region is coming from the gravitational lensing signal. You can look and see how much these background galaxies are distorted by the gravitational lensing. And so the blue is telling you where most of the mass is. So pink is telling you where the ordinary matter is. Blue is telling you where most of the mass is. And lo and behold, these two things are not lined up with one another. You can see that the blue, where most of the mass is associated with the galaxies. But most of the ordinary matter is in this gas. And so the conclusion then is that most of the mass has to be dark matter. Only about 5% or so of the ordinary matter is in the blue region. And so if that's dominating the gravitational lensing signal, that's where most of the mass has to be. Only a little bit of it is ordinary matter, and so the rest has to be dark matter. And we've seen several systems like this now, And really no one has ever come up with any other explanation. So there were a lot of people that thought maybe Newton was wrong, but they worked on what was called modified Newtonian dynamics. This pretty much killed off that line of research. Most researchers were convinced by this picture here that dark matter was indeed real. So hopefully I've at least given you enough evidence that you think I'm not just making this dark matter stuff up and that it is indeed real. And so if you'll accept that, well, the next question becomes, well, what is it? What's making up this dark matter? A priori, it doesn't need to be anything exotic. There's plenty of ordinary astrophysical objects that could potentially make up the dark matter. And these all fall under the context of machos, because astronomers, of course, love our acronyms. And so this one stands for Massive Astrophysical Compact Halo Object, which is just a fancy way of saying some ordinary astrophysical object. So for instance, red dwarfs, these are very, very dim stars. They give off less than 1% the amount of light that our sun does. And so if they're very far away and very, very dim, well then we wouldn't be able to see their light. So they'd be dark. Right? Black holes, well they're definitely dark, light can't escape. There are also things called neutron stars and white dwarfs. If you take our intro astronomy class, you'll learn all about those. These are basically dead stars that are not shining anymore. And so these are all ordinary things we expect to find in our galaxy, and potentially they could all perhaps be making up the dark matter. The catch is that we went out and we looked for these things. So actually one of the chief missions of the Hubble Space Telescope was to go out and search for these red dwarfs. The Hubble Space Telescope could see further than we'd ever seen before, and so we could see these dim objects that we thought maybe were out there. And Hubble just did not find enough of these red dwarfs to make up the dark matter. Similarly with the black holes, the neutron stars, and the white dwarfs, people figured out ways to go and look for these things. We figured out about how many of them there are in our galaxy, and there's just not enough of them to explain all of the dark matter. At most, they could only be something like 30% of the dark matter. So the other 70% has to be something else. Something new, something we haven't seen before. And so perhaps if it's not a macho, maybe it's a WIMP. So these are actually the most popular particle candidates. WIMP stands for a weakly interacting massive particle. So this would not be a standard particle that you've heard before, not a proton, it's not an electron, it's not made up of quarks. It's some totally new particle we've never seen before, some exotic form of matter. It interacts via gravity because it has mass, and we call it weakly interacting. So what do we mean by that? We mean that it interacts through what's called the weak nuclear force. So there are four forces in nature: gravity, the electromagnetic force, and the weak and strong nuclear forces. This guy only interacts through gravity and what's called the weak nuclear force. These are by far the most popular candidates among cosmologists. If you ask the particle physicists really like another type of particle that are called axions. And this again would be some new particle no one's ever seen before. And the particle physicists really like this because it helps them solve some fundamental physics problems related to weak CP violation. So if you don't know what that means, don't worry about it. I just mentioned this for anybody who might know what that means. So I'm going to focus here on these WIMPs. They've been what I've studied, and they are by far the most popular particle candidates for cosmologists. And so this WIMP would be some particle that interacts through gravity, and it only interacts through the weak force. And so this is going to make it quite hard to detect. We can potentially detect it by its gravitational effects, but that's why we think it exists in the first place. So that would be a circular argument. And so we need to detect it some other way. And so we need to detect it through this weak nuclear force interaction. And so the bottom line is, there's a very, very small probability that a WIMP will interact with you if it encounters your body. Most WIMPs would just go right through you, but every once in a while, one might scatter off a nucleus in your body. And this is the same thing for neutrinos that come from the sun, if you've heard of those before. And we can detect neutrinos, so we should be able to detect WIMPs too. And so how are we going to detect these things that we can't see? Well, there are basically three ways that we can go about it. We can go to a particle collider, like LHC at CERN, and we can smack particles together, and we can try and produce some dark matter in the lab. And we can do what's called a direct detection experiment, where we wait for these very, very rare scattering events to happen, and then we try and observe them. Or we can do what's called indirect detection, which is to wait for dark matter to annihilate, and then we look for those annihilation products. And so I'll address all of these individually here. So first, let's talk about collider experiments. And so investigating dark matter was actually one of the primary reasons for building the Large Hadron Collider at CERN. And one of the main things they were hoping to find was new physics beyond the standard model, including the dark matter particle. And so the way a particle collider works is we have to accelerate these particles up to very, very high speeds. And at CERN, they're capable of accelerating protons up to greater than 99% the speed of light. So just unfathomably fast speeds. We know, if you've probably heard of the conservation of energy, this is one of the fundamental laws of nature. We say that energy is neither created nor destroyed. It's always conserved. But energy can transform from one form to another. So for instance, if I lift up a ball, I can give it gravitational energy. And if I let go, that gravitational energy gets transformed into motion as it falls. And so energy can change forms, but it's not created nor is it destroyed. Now in 1905 or so, Einstein came along and he said, well, I realized that mass is actually just another form of energy, and that there's an equivalence between mass and energy, given by his famous formula of E equals mc squared. So what this means is that since energy can transform from one form to another, energy can transform into mass, since mass is just another form of energy. And so this is what happens in a particle collider. We accelerate these protons to incredibly high speeds so that they have lots of energy of motion. And then when they smack into one another, some of that energy of motion gets transformed into mass energy. And so it forms new particles come flying out of your particle collider. And we study those particles to see what happened in that collision. And so particle collider data looks crazy. It looks something like this, where this collision event happened here in the middle, and now all of these particles have been produced, and they've come flying out of my detector. And I need to try and detect all of them. And so they build various things that are sensitive to different types of particles, and they try and figure out how much energy and how much momentum all of these particles have. And so what would happen at CERN, potentially if you give the protons enough energy, when they smack into one another, they create new particles, and potentially one of those particles could be the dark matter particle. And so a dark matter particle is very unlikely to interact in your detector. So if you produce dark matter, it's just going to take off undetected out of your detector. You're not going to see it. If you've taken physics, you might know that energy is not the only thing that's conserved in a collision, but there's also something else called momentum that's conserved. And so what they look for at CERN is they look for missing momentum. They add up the momentum of all the particles that they see, and if they produce dark matter, they would be missing some momentum. They would infer that that's because they created dark matter, and based off how much momentum they created, they could try and figure out the mass of the dark matter and other various things like this. So that's avenue one. We could just create it right there in the lab. It's kind of unsatisfying because as soon as you create it, it would leave your lab never to be seen again, but at least you know you created some and you could figure out what the mass of the particle and things like this were. And so this is a very, very fancy graph showing the limits from the collider experiment. And the bottom line here is that they haven't seen anything yet. So they haven't seen the dark matter particle. They've only been able to rule out various combinations of the parameters. So here we're looking at how likely is the dark matter to interact with my detector, how likely am I to produce dark matter in a collision compared to the mass of the dark matter particle. And we just haven't seen it yet. They've ruled out all this space, but there's still lots of space left to explore. And so that will have to be left, unfortunately, for the next generation of particle colliders, whatever that might be.
Just because we come up with some missing mass, how would we know for sure that that missing mass should be associated with dark matter rather than with some other unknown particle? So
it would be missing momentum. So the only other thing that could escape your detector would be a neutrino, and it would not have nearly as much momentum as a dark matter particle because
there could be some other unknown particle. I'm not sure how we would clearly identify that as dark matter.
So it would be an unknown particle with characteristics consistent with those of a WIMP, I think would be the statement that you would make. It's the same thing with the Higgs boson though, right? They found a resonance that's consistent with a Higgs-like particle. So that's the nature of the inference you make. The next avenue then is direct detection. So in this scheme, we actually build a big detector, some crazy detector like this, and you fill it up with some inert substance. So xenon is a noble gas. It's very popular to put in these detectors. And you build this thing, and then basically you sit there and you wait. There's some very, very small probability that if a WIMP comes in, it will scatter in your detector. And if it does, it'll deposit a little bit of energy in there that you can detect to try and detect this scattering event. But if you build a big detector like this, you only expect something like 10 to 20 events per year. So it's a very patient game that you have to play to try and sit here and wait. And it's a very, very sensitive and difficult measurement to make. And so we have to make sure that we shield our detectors from all sources of background radiation. And so rocks, natural rocks are radioactive, at least to a little bit. Even a banana is radioactive because of the potassium in there, you might know. And so there's all kinds of background radiation here we need to protect our detector from. And so they tend to bury these things deep underground. This one's buried in the Grand Sasso mine. We also, it's very, very little energy that gets deposited in your detector. And so many of these also have to be cooled down to cryogenic temperatures, just a few Kelvin above absolute zero in order to make this measurement. And then we sit and we wait, and we wait, and we wait, and we hope that we'll see something scatter in our detector that we can detect the dark matter. Unfortunately, they haven't seen anything yet either. We haven't detected the dark matter particle yet. And so the limits we have here coming from the direct detection experiment, we can basically think of this as being how likely is the WIMP to scatter in my experiment versus what's the mass of the WIMP. A few years back when I was in grad school, people were getting very, very excited because 4 of these experiments had all reported that they had detected the dark matter. And while they weren't in complete agreement with one another, they were at least kind of close in the same region. So people got very excited about 5 years ago that we were detecting the dark matter particle. Unfortunately, a bunch more experiments came out that didn't find anything that would have. And so all of these detections turned out to just be noise. And so they've all been ruled out now. And unfortunately, we just haven't seen the particle yet. This is basically the parameter space we expect the WIMP to exist in, if it's real. And so we've carved out about half of this parameter space. These solid lines is what's been ruled out. All of this has been ruled out. The dashed lines are what we expect in the next generation of experiments. So in the next 5 to 10 years, we expect to carve out this portion of the parameter space. 2 really popular dark matter models predict that there should be a WIMP in either this red region or this green region. And so we've barely carved into this region of interest here. And so hopefully these next generation of experiments, those are lined up right with the region of interest. So if these models are true, we should detect this WIMP within the next 5 to 10 years or so. Below that is where you start to get noise from neutrinos. So we're really hoping that the WIMP is not down here, because then it's a lot harder to make the measurement, because you have way, way, way more noise. So we've carved out roughly half the parameter space that we sort of naively expect the WIMP to be in. We haven't found it yet, but I'm not too discouraged. There's still lots of room in that parameter space there. And now the third avenue for investigating the WIMP is what's called indirect detection. And the idea here is that the WIMP could potentially be its own antiparticle. And so if you've never heard of antimatter before, it sounds very, very science fiction. If you have heard of it, it was probably on Star Trek or something. But antimatter is really not that crazy. It's just regular matter that has the opposite charge. So an electron has a negative charge and a very small mass. Its antimatter particle has the same mass, but a positive charge. We have protons. There are also antiprotons that have negative charges. And so antimatter sounds crazy, but it's really not that crazy. The only thing that's crazy about it is there's no antimatter around us. And the reason for that is that when ordinary matter finds its antimatter partner, they annihilate one another into energy. So if an electron encounters an anti-electron, out comes energy, out comes photons. So the idea here is that the same thing could potentially happen with WIMPs. Occasionally one WIMP could scatter off another WIMP, and since it's its own antiparticle, they could annihilate it into energy. Again, this would be turning mass energy into, say, light energy, since the energy has to be conserved. And so if the WIMP annihilates, hopefully it would annihilate into ordinary particles that we could see. Hopefully it would annihilate into things like protons or positrons or photons, gamma rays, X-rays, etc. And so we can look for anomalous sources of gamma rays and X-rays, etc. that cannot be explained astrophysically. And then perhaps the source for these would be the annihilation of dark matter. And so this is a very popular avenue. This here is a picture of one of NASA's great observatories, the Fermi Gamma Ray Telescope. And one of its primary missions has been to look for gamma rays coming from dark matter annihilations. And so that's what we've been up to, but third verse, same as the first, unfortunately we haven't detected anything yet. So there have been some very, very tantalizing hints. There have been a few signals that are anomalous that people say might be dark matter, but then some other people put a fly in the ointment. They say, well, actually there's some really obscure astrophysics that could be causing this. And we just don't have good enough data to rule that out yet. And so there's been some tantalizing hints, but nothing definite. And so here again, I'm just showing, well, how often should dark matter annihilate? How strong should our signal be, basically, versus what's the mass of the particle? And again, we've ruled out something like half the parameter space here. This is the 2016 line for that Fermi experiment, and we're carving into the parameter space. This dashed line here is a canonical value. This is our favored theoretical value for what we hope this cross-section here will be. And so it's been ruled out at low masses, below around 100 GeV. We've now ruled this out, but at higher masses, there's still lots of this parameter space. So everything between this dashed line and gold line is all still allowed here. And so the conclusion is once again the same. There's been a few nice hints, but just nothing conclusive yet for the dark matter particle. Bill?
Yeah, well, what is your best guess as to what the dark matter particles might turn out to be, if there really are dark matter particles?
So if there are dark matter particles, I think the WIMP is by far my favorite candidate. And that's because the WIMP is very, very natural. So in the early universe, you know, if you've watched The Big Bang Theory, you've heard the song. So in the early universe, things are extraordinarily hot and very, very dense. And so in the early universe, things are whizzing around fast enough that it's like being in a particle collider, and you could produce these dark matter particles. As the universe expands, the rate of production would fall off. You'd be producing less and less of them because the density is decreasing, so it's less likely that these scattering events happen. And so as the universe expands, you're left over with some residual amount of dark matter. And the reason people like WIMPs so much is because if you just assume weak scale interactions, you automatically predict the right relic abundance, the right density today of WIMPs. And that's called the so-called WIMP miracle. It seems a little too good to be true that that's just a coincidence. Now, it's not compelling, but that's the reason why they're very well-motivated candidates, and that's why cosmologists like them so much. The particle physicists, I think, like the axions a little bit better.
It's all great science, but it still seems so much like the old theory of the luminiferous ether.
So I would say that that's possible. I mean, we might have the physics wrong. That definitely could be. We definitely can't rule that out until we detect it. But you could have said the same thing about the Higgs boson for 50 years until we finally discovered that too. So the fact that this has been an open problem since the 70s isn't too discouraging, I think. But we should be open-minded to the possibility that there is no dark matter for sure.
Yeah, once we get some verifiable, repeatable evidence, I would definitely become less skeptical.
Sure, yeah. So you're definitely right to keep an open mind here. And so based off all this, then, how would I wrap it up? Well, we haven't detected the WIMP yet. We haven't seen it. Some people are starting to get a little bit discouraged because basically for the last 20 years, everybody that's given this talk has said, oh, in the next 5 years we'll find the WIMP for sure. And 5 years later we don't find it, but the next generation is just as confident. And so here I am in my hubris, and I'm also pretty confident that we'll find it in the next 10 or 15 years, if it's real. And so we've carved out about half of the parameter space here where we expect the WIMP to be. The next generation of experiments will carve out most of the rest of that parameter space. And so I would say if we haven't seen it in the next 10 years or so, then there will be a lot more skeptics, Dr. Brown, because I think at that point this scenario will become disfavored and we would start looking for a different solution to these problems.
I was just watching, listening to NPR last week. It was about some device that apparently the particle physicists are building in Oregon. Something where they're hoping to be able to detect, I think it was the axions. That sounded like an interesting undertaking that they were doing.
Yeah, so axions are the candidate I didn't talk about, and there are lots of ongoing experiments. I think I heard the same one. It's a microwave cavity that they at the University of Oregon, I think.
Some cavity that down to like half a degree above absolute zero. Trying to keep it cold and detecting it somehow.
Yeah, so axions are really interesting because they help us solve the problem of why are we here. So in the early universe, I said, you can create matter, but anytime you create matter, you also have to create antimatter because there's something called conservation of charge. You can't create charge out of nowhere. So if I create a proton in a collision, I also have to create an antiproton. And now, later on, that antiproton finds a proton and it annihilates. So now there's energy and no matter left. And so, how are we here then? We're made up of matter and there's no antimatter in our universe. And so apparently there must be an asymmetry. Somehow you created more matter than you did antimatter. And after all the antimatter annihilated away, we were still leftover matter that makes up us and the galaxies, et cetera, et cetera. And so this is a huge, big fundamental problem. It's called weak CP violation. And axions help solve this. That's literally all I know about axions.
What are some galaxies recently discovered that don't appear to have any dark matter?
So I know there's been various claims of some galaxies that are at least not dark matter dominated. I don't know if they so globular clusters are the really interesting systems because they show no evidence for dark matter at all.
You got shear down as one of the reasons. How does that go?
The cosmic shear?
Yeah.
Yeah, sure. So in the universe, we have all these galaxies.
Could you do us a favor and switch to a darker marker, please? Oh, there, okay, that'll work. Thanks, Bruce.
Actually, I bet if I can just Google a better picture than I can draw. There's nothing incriminating in my browser. Yeah, so here's actually this sort of idea of shear here. Maybe I can get an even better one with it. So this is kind of the idea. This is one of the classic pictures for cosmic shears. That structure in the universe makes up this huge web of galaxies. And when we look out in the universe, we see, I'm just going to draw elliptical galaxies because ellipticals are easy to draw. And so you have, say, a bunch of galaxies, and these alignments should just be random. There shouldn't be any preferential alignment or anything here. But if you have gravitational lensing due to mass, then that tends to shift things and turn them towards your gravitational lens. And it tends to stretch the shapes of the galaxies. And so it distorts the shapes and it changes their alignments. And so by looking at the amount, you can figure out how much matter was along the line of sight. So it's an integrated line of sight measurement that you're making to say how much matter is along that line of sight. And now I can compare this to how much gas and galaxies are on that line of sight. And I can say, well, it looks like there's more matter here than what I'm seeing. So it's the same story over and over again. You go and you make a measurement, and you always infer that there's more mass than what you actually see.
Back to your very last point about the 15 years, like that we may discover it in the next 15 years. Is that reliant on just an expression of time, or like are we confident that we've invented the components to detect it, and we just need the time to run these experiments?
Yeah,
or-
so that's based off actual experiments that have been funded, or are either currently collecting data, or should start, or the next generation after. So current plus the next gen. So experiments that are running now, plus the ones that have been funded and will run. We don't count the ones that haven't been funded, right? Because they probably never, might not ever will be. So just based off active experiments, we'll carve out that parameter space in about the next 10 or 15
And
years.
we're also confident that we're working with like a finite degree, that space on the graphs that you showed, that is a limited quantity.
If it's a WIMP, so if it's a weakly interacting massive particle, then we expect that the scale should be around the weak force scale. And so at a certain energy, the weak force and the electromagnetic force split, the symmetry is broken. And so that's the motivation, is that the WIMP should be created at that scale. And so that sets sort of your, that's your null hypothesis, I guess, is that the dark matter should be in that range if it's a WIMP. If it's an axion or something else, well, now all bets are off.
Oh, that would change
So-
that.
I specifically, when I say that 10 to 15 years, specifically mean for WIMPs. Now, you could rule out WIMPs without ruling out dark matter, which sort of gets to this chasing your tail idea that Dr. Brown had mentioned. So you really have to rule out all the dark matter candidates before truly ruling out the dark matter hypothesis. But the WIMPs really, I think, the best motivator.
Thank you.
Other questions? Let's thank our speaker.